So presently, I'm working on quantum gravity phenomenology, which is pretty much the same topic I've been working on for the last 10 years. Right now, I have a grant from the Foundational Questions Institute to work on space-time defects. So one of the biggest questions in quantum gravity is whether space-time is fundamentally smooth, continuous manifold, or whether it's fundamentally something discrete, like some kind of network or graph that only approximates the smooth background that we have in general relativity. So arises the question, well, how could you find out? Now, directly testing for this discreteness is basically impossible because it's somewhere at the Planck scale, so it's way beyond anything that we can measure. At least that's what I say. Okay, so some people might disagree with me, but okay, then we get into this whole topic with Lorentz invariance violation, so let's forget about this. My idea was that instead of directly looking for signatures of this discreteness, why don't we look for something that's less controversial, which is that any discrete structure that you can think of would only approximate space-time imperfectly. There should be some defects that are left in the same way, pretty much in the same way that you have defects in crystals.
Oh, very cool.
It's just because anything in nature is imperfect. Right. So if something is really perfect, you need a strong reason for this, and there isn't any such reason. So if space-time comes about from some underlying discrete network or something, you should have some deviations from general relativity that reflect themselves in these defects. So then there's the question, well, how do you look for this? Well, the first thing you need is a model, a phenomenological model that takes into account these deviations from general relativity. And some years ago, I wrote a paper that lies out such a model. Actually, it's two types of defects, and there are two papers, but that's not so relevant right now. The problem with these papers is that they only work in flat space, and if you want to do cosmology, astrophysics, you also need to do it in curved space, so you need the full apparatus of general relativity. So what I'm doing right now is that I'm trying to generalize this model to curved backgrounds so that I can look at cosmological observables. So these defects should generally affect the propagation of particles in space-time because they would scatter on them. Even if they are very rare, these defects, if the particles propagate over a long time, say they come from a gamma ray burst several gigaparsecs away, something like this, these effects should add up, and they're not a priori entirely unobservable. But to say whether they are observable or not, you need a model, and you need to calculate something, and then you can put constraints on the parameters, and that's how it works.